Hi, everyone. Good to see y'all. Just gonna wait a few minutes for everyone to trickle in, but feel free to just chat and hang out for a bit. Did anyone do anything fun over spring break or this past weekend or week, I guess? I'm curious to hear if anyone had some novel experiences.
Unfortunately not. I was stuck at like a cafe the whole week doing homework and stuff.
Prize and homework. Yeah, it's a bummer. Very cool. Skydiving. That's interesting. It's different. Lots of adrenaline. I laid around and did nothing. It was really nice. Um, I had off from work too, so it was great for my day job. So it was nice. Had some time to sleep in, which was good. Oftentimes I have meetings at 7 a.m. So having the ability to sleep in until 9 or 9:30 was glorious. Um, yeah, spring cleaning. Yeah, it's sounds about right. Also doing some of that. So let's jump into it. I'll share my screen and we can kind of talk about kind of what's up in the class and then jump into lab or lecture and then lab. Sorry, I have so many like windows open. That's why it's taking me a second to figure out what to share. Okay, let me open the chat just so I don't miss it. Great. So today it's kind of continuation of where we left off last week. In case you weren't here on the 30th, it's kind of crazy to think about already. It's in April. The lab from that day was due today at 9 a.m. The submission is still open through the end of the semester, but I will be deducting points. So please do get that in as soon as possible. We didn't have class last week, and so now we have class this week. Today's the 13th. Yes, just verifying that. Um, and we're going to be jumping into more spatial aspects of doing things with Python, specifically vector data. So hopefully this is a little more interesting and relevant to all of your kind of uh, foci in this GIS program. But it's still going to be kind of, uh, I wouldn't say introductory, but kind of not as meaty. We're still kind of learning the basics. I mean, you're not all like engineering students, and so I can't assume you have all this programming background. And also, this is not like a programming degree. So we're easing into it, building our confidence. But today should be a little more interesting than the first week. Um, The lab from today will be due next Saturday before 9 a.m. So a slightly faster turnaround time, but I have total faith in you all that you'll be able to finish. And don't hesitate to reach out if you have some kind of extenuating circumstance that requires an extension. Like I'm a generally reasonable guy, just like let me know. And then in the coming weeks, we're going to kind of really dive into raster data and more kind of traditional remote sensing type data formats and learning how we can use Python to not only just the mechanics of analyzing that data, but then also building intuition for how we can use Python as a broader problem solving toolkit to maybe compare different data types, ask questions about the natural and built environment and that kind of in between space, and seeing how it's really just another tool in our tool chest as creative problem solvers. So I was looking at my calendar earlier this week, kind of had a moment of like, oh crap, like the semester is really short. So if at any point you're feeling kind of overwhelmed or anything, do let me know. I'm here. I'm not like a counselor, but like reach out, let me know if like there's too much course load and we can have a conversation and see where there's accommodations that can be made. And this is also broadly as a course, as a class. Um, if you collectively come together and let me know, like, can we like slow down a bit or speed up? I'm super amenable to that. So if you all want to do like a student labor union as students of this class and have a cohesive message, that works too. But just needless to say, reach out if you're feeling overwhelmed or not. And I don't want you to feel stressed. I mean, life is stressful enough. I'm not going to just like auto pass everyone, but there's ways where we can kind of reduce um, things or increase things if you want more. So really do just let me know. And I'm happy to throw things your way if you're like really interested in programming and want to dive deeper. Do reach out. Um, but yeah, that's about it for the schedule updates. So don't forget to turn in lab one. And today is all about lab two. I've updated the course website with a few new links, namely the slides for today, and then a link to the video recordings from, I guess, this whole semester. So this will be a playlist that I continuously update throughout the semester with each new class recording. So this is an easy way to access it. Also, just going to YouTube. I'm not trying to get you to subscribe to me. Like I have no monetary incentive from that. It's really just convenient for you to view the content. So whatever works for you. Um, but yeah, that's about it. Am I going to delete all the recordings after the semester ends? Heck no. That's going to be there until YouTube takes it off. So that'll be a resource if you want. If there's concerns about privacy after the semester, not wanting to be on there, do let me know. But I feel like there's nothing really that um, sensitive or problematic that we cover in this class that you'd maybe not want your name to be associated with it. And yeah, to me, it just makes sense as a long-term reference source of things that you learned and maybe if you need a refresher. Cool. Um, that being said, are there any questions so far before I jump into lecture? And those could be questions from like the assignment, from just generally about the class, about tech. We can also have like an open QA at the end of class after we finish the lab exercises, but I'm just trying to basically open the floor and make this not just me talking at you for 3+ hours. Uh, I'd rather have a conversation, especially if there's ways that I can benefit you all differently besides just Python-y things. So if there's ever like career questions, whatever, don't hesitate to ask. Some of you have reached out already via email about like an interview kind of thing. Happy to do that stuff. Also happy to just chat about my pivot into tech from GIS proper to tech more broadly. I think that's another, um, let me say, uh, a benefit of having an instructor like me who's not just a PhD professor the tenure life. I tried to do a PhD, dropped out, wasn't for me, but I've been working in industry and I have that perspective of what it's like for people that have jobs in like industry. So don't hesitate to reach out. Um, doesn't seem like there's any questions. Also, I was blabbering, so I'll leave a few seconds and then we'll jump into lecture. Okay, sweet. Um, I'm going to unshare my screen and then reshare it so that I don't have to do a bunch of craziness. So just give me 1 second. Vector spatial data with Python. So fun. Sorry for the absolutely horrendous design. I am not a designer, or graphic design is not my passion. Um, Neither is making presentations. So uh, I figured short and to the point without too much input is probably for the best of everyone in this situation. But if you want a little color, don't hesitate to send recommendations for fonts or memes. Yeah. In my work, I use memes more in presentations. Here, maybe I should use some more memes. But yeah, I agree, Gareth. Simple is best sometimes. Um, oops. So today, I'm not gonna, it's gonna be a super short lecture because the more and more I reflect on my experience as a student, the more I ready to use and requires no effort. Yeah, I know, Talissa. I feel you. I guess it's more the choice. There's too many choices. I need I need the AI to just pick for me. Um, so today I'm trying to distill lecture into really just setting the framework for what we're gonna do today in lab. Because to me, that's the main attraction. That's why you're here. That's the actual skills and experience that are valuable that you're going to be able to put on your resume, talk about in interviews with hiring managers. It's actually coding, doing, building stuff. Um, Me talking at you in lecture for an hour or two. Um, it's great, I guess. I don't like talking that much. And I think that you all probably would rather do other things with your time on a Saturday morning. So tell me otherwise, and I can make lectures a little longer, but I think that in general, it's probably more fulfilling and interesting for you all to just jump into lab. So today we're going to cover just basically the vector format of spatial data and kind of how Python allows you to read it, write it, maybe. We'll see. I don't know if we'll get to that today. And then kind of understanding attributes about the data that are really like foundational, like coordinates, reference systems, projections, stuff like that. So the spatial metadata. And then finally, performing common kind of GIS type operations with vector data. So I think we'll do some things like dissolving, maybe some unions, stuff like that. So the things that you'd use a traditional desktop GIS software for, where you like click a drop down menu, have to fill out a little user interface where there's like text inputs. You have to pick the different layers, select which kind of method you want to apply to it. You can just do that with code too. And like the Arc suite of products let you do that with like the ArcPy utility, but you can also do that using just entirely open source software too. So today we're just going to be using all open source things. But I do encourage you to um, if you are so inclined, try to replicate these exercises using some Esri software or QGIS, you know what I mean? And their Python extension. To me, that would be like demonstrating absolute mastery, like next level wizardry. If you can do that across like softwares, you can talk to like hiring managers and just be like, I'm legit. Um, and so that's really the overview for today. Hopefully that's a little more exciting and provide some value for you all. Before we jump into lecture, I do want to say that I'm going to be incentivizing attendance throughout the semester. And one of the ways I'm going to do that is through these in-class code words and time-limited point opportunities. So this week's code word is yucca brevifolia. Um, so on Canvas or whatever it's called now, you can navigate to the assignments and you'll see that there's like a code word or something for lab 2. And so that's where I strongly encourage you to put in this code word and you'll get 3 points. It's a time limited opportunity. So you can only submit between 9 a.m. and 1:30 today. And is this a scientific name for a plant? Yes, exactly. The Joshua tree. So I live in 29 Palms, which is right next to Joshua Tree National Park. And so that's kind of going to be the theme for many of these code words throughout the semester is the plant life, maybe the bird life of my surroundings. Also separately, if any of you are ever in the Joshua Tree area, hit me up. Let's get coffee. Let's chat, GIS, whatever. Happy to connect. But yeah, let's get it. So you get those points. Make sure you submit them. Try to make it easier today so you don't have to email me and then, or easier for me too, so I don't have to do that. But just submit that assignment, get your points, and more to come throughout the semester, as well as other opportunities to demonstrate that you're participating, learning, and can earn points. Let's get into the code. Unshare. Are there any questions before I jump in? Cool. Don't hesitate to like unmute throughout or to write in chat, and I will do my best to answer. Let's share it. Cool. So here's the lab for today. Very similar kind of format or expectations compared to last week. So it's really creating a public GitHub repo, using another repo as a template, then using GitHub code spaces to perform do code things in the browser. So you don't have to install anything locally. So it's just convenient for everyone. And then this week we have 9 different lessons. Some of them actually don't involve code. I think it's more just like reading. And so we'll go through those all today. And I also view those as kind of like a substitute for lecture because we'll be going through and kind of learning more. And I'm not going to be skipping over as much of the content today. And then throughout, we'll be committing our changes to the repo. And then once we're done, we'll submit our URL in Canvas. Also, you can submit your URL now and just keep adding to that repo. So you don't have to wait until the end to submit the URL if you'll forget. So whatever works for you. Just wanted to put that out there. But I think that this is very similar to last week, except we'll be using a couple different libraries, more GIS focused ones. So hopefully that's a little fun, but I'm gonna start just following the lab. At this point, if you work better independently without someone talking over, don't hesitate to drop off. I encourage you to work in the best learning environment for you. And if that's not while I'm talking, no harm, no foul. You do you. You're here for the Yucca brevifolia code, and you're going to turn in your assignment on time, so we're good. But if you want to stay and hang out, I'll be here working through these labs, and let's get it, in the words of Viviana. So I'm going to start by creating a public GitHub repo called GIS605 Lab 2 in my GitHub account, using this repo as a template. So I tried to do a little better this week and actually provide the link so that it's easier to notice. I'm going to now open this link. So we're here. We're going to use this as a template. I'm going to copy the instructions from, or the name, so I don't mess it up with the typo. I've noticed that this is easier for most people. So I'm just copy pasting that GISC 605-lab2. And then let's use this as a template, create a new repository. We're going to put it in my account. For you, it'll be a different username because you're not me. And then we're going to call it GISC 605-lab2. And then make sure that you select public, and then we'll create the repository. So at this point, I'm going to move these instructions to a separate part of my screen, just to make it a little easier for me not to have to toggle back and forth, and so that you're not having to see me toggle back and forth. But this is when having multiple screens or just a split screen situation is pretty helpful. So we have this repo created, GISC 605 Lab 2. It's in my account, generated from this template repo. Let's now open it in a GitHub code space. So we're going to go here. We're going to just create a code space on main. So it might take a few moments to initialize, but then you're presented with the beautiful kind of, this is almost identical to the Microsoft Visual Studio Code user interface, which is a pretty common developer kind of code editor used in industry and academia. And so Microsoft owns GitHub. And so that's why there's a lot of kind of interoperability design kind of language similarities. So you can see that this kind of workspace is automatically installing everything that's in our requirements.txt file using a pip utility. And so it just does this on startup. So you can see in this requirements.txt file, there's a few Python libraries that are already there. We're going to kind of do an alternative way to install things and actually manually run pip commands ourselves once this is finished installing. So in step 3, I show you how I included a command for installing GeoPandas and EarthPy using pip. So we're going to try that out now. And you're going to type into the integrated terminal that's located in your GitHub code space. So pip install GeoPandas and EarthPy. So GeoPandas is this kind of geospatial extension to pandas. And you can see that as we're installing GeoPandas, pip knows to install any other relevant dependencies, like Fiona or PyProj or Shapely. And then likewise, when we're installing EarthPy, pip knows to install raster.io, scikit-image, and other relevant kind of dependencies. And so that's super nice.
I have a question.
Yeah, what's up?
So at what point would we connect the kernel, like to start it with Python?
That'll be coming up in a sec.
Okay, thank you.
Yes. So yeah, we're preparing that Python workspace first. So that's why, I mean, we could have done this by modifying requirements.txt, which we'll probably do next week. But I just wanted to demonstrate one of the ways to update your kind of workspace with new libraries. But then we're going to start the kernel once we create the new notebook files.
Got it. Thank you.
Yeah, you're welcome. So in that vein, let's create a notebook file. So I'd encourage you, don't create it in notebooks. I mean, you can, but like just create it in the root here. You can do new file. You can also use touch. I'm gonna use touch because why not? So we're gonna touch intro to vector .ipynb, and you can see that a new Jupyter notebook was created here. Let's now click to open that. This is where it's detecting the kernel. Now we have to select the kernel, which is what Talissa mentioned. So we're going to click Python environments and then select Python 3.10.13. And so now we're good to go. If anyone runs into issues, do let me know. I'm going to kind of make this a little smaller just so we have more visibility here. All right, so I'm going to open Intro to Vector Spatial Data. And then I'm going to bring this over here so we can look at it together. So this is the first lesson in this kind of module of GeoPandas from CU Boulder. I think that's the CU Boulder, or Colorado generally. And so we're going to learn how to work with spatial data in vector format. So importing, manipulating, and mapping shapefile data. What we're learning here isn't limited to just shapefiles. You can apply a lot of these same techniques to other data formats like GeoJSON, the miscellaneous like geodatabase formats you can also read in. And so these kind of generalized tools can be slightly tweaked for other data sets or other data types. And then we're also going to learn about how to reproject vector data into different coordinates reference systems, like I mentioned before. So we're going to learn about, or I'm assuming you all know about the different kind of vector data types, but we'll have a quick refresher, and then we'll jump right into how to use GeoPandas to open those different data types, view spatial metadata about those data, and then display them using some kind of graphing library like we did last week. So I'm going to skip over this downloading the data set because we'll just do it in line with the code in a bit. But here is our quick jump into vector data. And so as a reminder, there's three different types, common types of vector data: points, lines, and polygons. They're kind of comprised of vertices that define the shape of the spatial object. So these points are kind of those vertices that can be used to have like a single instance of something, like a tower location or a sampling location. Then you can have lines where there's at least two vertices connected. That's something like a road or a stream network, or just a single stream. And then polygons could denote like a closed boundary, something like a building, maybe a watershed. So these are three common vector data types, and this links out to a figure from NEON, which is the National Ecologic Observatory Network or something like that. And it's a National Science Foundation funded project to do a lot of kind of continuous monitoring of parts of the US, like certain ecosystems. And so they have high frequency kind of climate sampling, these kind of like tower locations to detect meteorological data, but then also they're taking remote sensed imagery from both airplanes and satellites. And so it's an interesting kind of application of remote sensing. So a common data format that's used to describe these data types, at least in the kind of the Esri world, is shapefiles. More and more, if you're kind of living in web, like internet web outside of Esri land, people don't really use shapefiles as much. There's things like GeoJSON and just other data formats. And so it kind of depends on where you're dwelling. But the shapefile is very common, and shapefiles are actually comprised of a few different files. And so GeoPandas magically lets you just read in all that data without having to worry about it, kind of like other desktop GIS softwares. Um, so we're going to learn how to do that very shortly. But you can see some of the files that a shapefile will have. One of note is the PRJ file, and this is something that we're going to be inspecting a little bit later today to display metadata about our spatial data. And then it's important to share all those files when you're sharing a shapefile. I'm sure you've all had that painful experience of not sharing everything and someone can open it, or you were on the receiving end of an incomplete shapefile. So do make sure to share them. That's kind of one of the limitations of shapefiles is they're kind of annoying, but you have to share all those separate files. There's other ways where it's just a single thing that are kind of more simple. So let's jump into some code, I suppose. I'm going to return back to my code space. Let's import some packages, namely OS, matplot, lib.pyplot. And we're going to use import aliasing so we don't have to write matplotlib pyplot every time. We can just say plt and Python will know that that's what we mean. We're going to import GeoPandas as GPD, another instance of import aliasing. And finally, import EarthPy as ET. So let's import all these, see if we run into any errors. At this point, do yell out if you've run into any errors where your Python environment is not able to import GeoPandas or EarthPy, as we're going to be using them all throughout today's lab. Okay. Now let's download the data. We're going to use the EarthPy data get data kind of method. And then we want to download the spatial vector LiDAR data set. OS. And then we want to set our kind of home working environment for where to store things. This is all kind of review from last week. So hopefully nothing looks terribly new yet. You can see it's downloading data. It's going to store it in this kind of cloud computer environment. Cool. Now let's read in that data with GeoPandas. So we're going to be looking at the San Joaquin field site. This is part of that neon observation network. I realize the link is broken in the lab. So I'm trying to Google. But yeah, this is the San Joaquin site is somewhere in New Mexico, I remember. There we go. The San Joaquin experimental range. Oh, it's in California? Oh, I didn't realize that. Good to know. But you can see there's a bunch of different data that they have. They're collecting observations about the wildlife, the like birds, the insects, the rodents, but also plant life, how things are changing in response to environmental change. And so we're going to be studying this site today or learning about this site. We can see it's north of Fresno, kind of near the Mammoth area, I think in the Sierra Nevada mountains. Yes, cool. So let's plot that data. Plot centroid. So we're going to plot the centroids. Path join data. Spatial vector LiDAR, California, neon SJER site, vector data, SJER plot, centroids.shp. And then let's import that with GeoPandas, because that's just specifying the file path. Let's actually import it. So we can do GPD, read file, and just plot centroid path. And then let's show the first 5 lines using the head utility. So you can see we have an error. I forgot to put an equal sign there. No biggie. Python lets me know I messed up. We can fix it real quick. Now we can see that I spelled something wrong. It's also no biggie. It happens. It's pretty cool though. We read in some point data. We can see the plot ID. We can see some location information outside of the actual geometry column. And then we can also see the type of, I guess, land cover there. So this data set actually has a good amount of information. So now let's display information about this data set. Let's inspect it actually. Let's do SJER plot locations. What happens if I just do info? That's ugly. It's not as bad. So nothing is null. We can see that the object type is it's sort of equivalent to a string, not exactly, but close enough. Is there a shortcut to create a new cell block? In terms of keyword shortcut, I am not sure. If you're in a cell, you can run a cell using Shift Enter, and then if you just do that a bunch of times, it like aggressively creates new ones. So maybe that's what you're looking for. But practice the pinky ring finger combo of Shift Enter, and you can get fast at it. Hopefully that helps. There might be like a shortcut I don't know about. Oh, so it's on Mac, it's Command Enter. So I guess here, let's see what happens. No, that doesn't really interesting. Okay. So for me, Shift Enter seems to work better. I'm also using a Windows keyboard on a Mac, so that could be why some of the things are not perfect. Let's try to just look at let's look at the describe, or no, let's do info. Let's now check out just the plot type. I'm curious about the plot types. This is kind of the exploratory data analysis. So you can see it didn't like this actual syntax. Let's try describe. It's been a minute since I did this. Okay, cool. Okay, so this just describes okay, nothing too exciting. We'll learn some more throughout today's lesson. So let's actually jump into spatial metadata then. First, we'll learn about kind of the type of our data set and then slowly dive into different tidbits. So let's do type. I already forgot the name, my goldfish brain. So it's a GeoPandas geodata frame. These are similar to the pandas data frame, but just with a geometry column, essentially. So it's nice because you can do spreadsheet type operations on GIS data, which is kind of cool. And think about like a shapefile, like a spreadsheet. I mean, you can do that in other software too, but for me, it was pretty cool learning about GeoPandas the first time. So geodata frames have a bunch of different attributes that you're able to invoke that kind of describe spatial metadata. So two of them that we're going to check out right now are CRS and total bounds. So to start, let's do CRS, and we can see the projection, EPSG 32611. It's in WGS 84, UTM zone 11 north. We have information about bounds, lots of valuable spatial metadata, especially if you're trying to do an analysis. You want to compare metadata to make sure things are lining up well. Another one that you might encounter is total bounds. And this is really kind of just a numerical definition of the outer kind of extent of this data set. And so if we look at the lecture or the kind of Colorado resource, we can see the total bounds, how it's described here as like the square that can encompass all items contained within the data set. So the edge, the furthest north, south, east, and west. Cool. So another thing you might want to inspect is the shape of your data set. So like how many features are in your data set. You can do that using the shape attribute. And then finally, or not finally, but another kind of really common operation that you're going to want to do is plot your data. And GeoPandas provides some super useful built-in plotting utilities. This isn't super beautiful, but you can see how this is the foundation for creating a figure. I've seen lots of really cool like website or academic article tier figures created using Python. You can do some really amazing kind of scientific design thingies. And they can also be interactive, which is pretty cool too. So let's actually make this a little prettier looking. Not too much prettier, but a pinch prettier. And to get some experience, more experience plotting, because we did plot last week using PyPlot. But let's do some more. So we're going to use PyPlot to create a subplot. It's really just like a helper or it's shorthand. We're not going to have multiple subplots. It's just going to be this one data set, but subplots is kind of a nice wrapper that streamlines certain things about making figures. So you might see that throughout this lesson and even this semester. So let's take the plot locations, and now we're going to plot it on this figure item. And so after I type out everything, we'll kind of walk through line by line. So here we're creating a figure and an axis using this PyPlot utility, and it's going to have a 10 by 10 size. Then we take our data set up here, this kind of these records, and then we're going to plot them on the axis that we created up here. This just gives us a little more control, fine-grained control of how to display things. In this example, it's going to look pretty identical to the one we just did using just plot, but PyPlot gives us a lot more fine-grained control over colors, shape, how to render things nicely. So you can see these look pretty similar, but we're just able to kind of change the size a little more easily. And so you can get pretty fancy pretty quick. So let's skip the following one because it's kind of identical. But now let's actually plot using one of the categories contained in the data set. So PLT subplots, oops. Again, fig size equals 10 by 10. And this is nice if you have some kind of specific shape you need to create, like for a journal article, you can kind of impose some kind of aspect ratio or just like shape of the image. So we got SJR plot locations. Let's plot it. Let's do column equals plot type. Oops, spelling today, man. I'm using a keyboard. It's an ergonomic keyboard, but it doesn't have lights. And so I can't look down and see like if I'm typing on it. So I'm trying to have it vibey in here and be a little moody with the dark lighting, but then it's hard to type. The pains. So then let's set it to categorical equals true. Let's put a legend there. And then inside that 10 by 10 kind of figure, let's make our actual image 10 by 6. Let's set a marker size so it's easy to view. And let's use a color map called set2 for categorical kind of data types. And then we want to put it on the axis. So ax.setTitle will let us set the title of this data set. SJER plot locations. And then /n is actually kind of this shortcut keyword for a new line. So when this renders, it's not actually going to show the /n. It's just going to do a new line underneath SJER plot locations. And then Madera County will appear directly below. And then let's do plt.show. And you can see you have our title with a line break. We have a legend with our 3 categories of data. And you can see that where the data is occurring throughout space. If you wanted to go even further, you could render a base map, perhaps, but we're not going to do that today, or yet, at least. But before we finish up this little lesson, let's do a couple more, I guess, not graphic design, but more cartography type things of changing marker sizes, all that goodness. So again, if I was trying to be super efficient, I wouldn't be typing out all this. I would be copy pasting, but it's good to get practice. It's good to show you that it's okay to make mistakes and gracefully recover. So let's again use the plot type column, set it to categorical equals true because we know it's a categorical data. We want to display a legend. Now let's use a star marker, and we can denote that using the asterisk symbol. And let's set a marker size equals 65. Let's use a different color map this time, orange to red. And there's resources online that will give you all the shortcuts or the keywords for the different color maps. I'll answer your question in a second, Talissa. Let me just finish typing so I don't make a typo. What locations? I can sort of multitask, but not really. Cool. Now we have stars. Fancy. So Talissa's question. Why can some items be squished together with an equal sign and some need to have a space? So it's really more stylistic than anything, because you could do, I think this will all work. I think this is what you're getting at, Talissa, right?
Yeah, that's exactly what I mean.
Yeah, it's arbitrary. It's really, and that's kind of annoying and frustrating, but it's more, I think, convention than anything. I know Python has specific rules, but in my experience, you'll most often see the space around this sort of equal sign. but then oftentimes people will just omit the space here in this context. So it kind of just varies. Um, but they're both correct in the sense that you won't get an error, if that makes sense. And
Got it.
hopefully this
Thank you.
demonstrate that. Yeah. Yeah, you're welcome. But yeah, it's a little wonky. And then as a final, I guess, example for this notebook, let's plot two data sets together. So separate shape files. So let's read in some data. Um, so we're going to have a cropping layer. Crop extent path. Data. Spatial LiDAR. I'll have to find some Joshua Tree related data for the semester. Cool. And then let's just cool. Just quick type it up. There we go. So you can see it's just a polygon. Very cool. Let's actually see what it looks like before we plot it together. So it's straight up just a square. Okay, cool. Or rectangle. Um, let's plot them together. Let me get some coffee first. Okay. Okay. So for this, let's set the color equals light gray of at least the inside of the crop extent. Let's set the edge color to be black. Actually, no, let's make it a little obnoxious. Let's make it purple. Let's make this. Let's make the inner color pink. Maybe obnoxious is the wrong word. Colorful is the right word. Let's set a transparency of 50%, and then we'll plot it on the AX axis object. Next, let's add another layer to the same AX axis object. So we're going to take our plot locations. Then again, plot the plot type column. Specify that it's categorical. Use a star marker. Specify a legend, a marker size, and a color map. Now let's set the title. Let's turn off the tick marks of the axis so that it's a little prettier looking. And make it kind of more equalized looking. Ah, spelling. And then display it. And see we have a lovely little figure with two data types, or yeah, a vector or a polygon and points. And we're able to display them both. That is it for this first lesson. So I'm going to save everything and commit the changes to the repo.
Do you mind scrolling back to the code for a second? Sorry.
Yeah. And also all of this is in the earthdatascience.org website. I'm just maybe tweaking a color here and there. So you will have that resource too, separately. Let me know when it's good to go.
You're good. I didn't realize it was the same thing.
Okay, for sure. Yeah, no, I'm just it's the script, but I might go off script a little bit here and there, but it's still generally the script. Cool. So let's commit and sync. Would you like to stage all your commits? And yes. Finish lesson 1. Close that. Let me close this. Let's leave this tab open. Oh, now we can return to our GitHub repository, refresh the page, and we'll see that we have a new Jupyter notebook there with everything we did in this lesson. Cool. Let's jump into the next lab or sublab. So now we're going to do intro to coordinates reference systems. So we did a little bit of a sneak preview in the previous lesson, but now we're going to dive a little more in. So I encourage you to check out this video at your leisure. I don't think it's, oh, that's loud. But yeah, I'd encourage you to watch this, but I'm gonna skip over because I don't know if Zoom is optimized for that at this point. But this video just highlights how continents can look larger or smaller than they actually are, depending on the projection. So coordinates reference systems allow us to define the location of something in kind of relative space. And so you can see that this coordinate system is two-dimensional, but we live in a 3+ dimensional world. And so these flat maps are kind of, there's limitations to them in terms of representing curved things in space. And so a flattening has to occur. And so really the CRS is a definition of how the flattening is occurring and kind of what to consider or give you an idea of what places might be affected more. And so that's why there's so many different CRS to kind of specialize in certain geographic regions or to minimize specific kind of limitations of projecting. And so a CRS is comprised of a coordinate system, the XY grid, horizontal and vertical units. So like feet or meters or inches, the specific datum. So which version of the Earth shape they're using as the kind of reference point in terms of like, there's different models of how the Earth is shaped. It's not this perfect sphere that's nicely depicted on globes. It's this weird kind of like funky looking mass. And so that affects how things are projected, depending on which model of the funky kind of blob of Earth you're using. And then finally, the projection information is the math stuff that defines how to flatten objects that are on the round surface so you can view them on your computer screen. And so this is important because different data stored in different systems. If you want to do any kind of analysis, you need to really understand how to uh, line up your data. Certain programs will do projection on the fly, but that doesn't always, uh, not all software does that. So you shouldn't necessarily rely on that. And so uh, having a better understanding of how to project or reproject data will serve you well in your careers. So with that being said, let's get some practice. I'm going to again move this over, jump into, let's create a notebook called, actually, what do I have to call it? Intro to CRS.IPYNB. Okay. Oops. Wrong shortcut. Okay. So again, let's select the Python 3.10.13 kernel. And we should be good to go with all the dependencies we've already installed. Let's import a bunch of stuff. Import OS, import NumPy as NumP, import pandas as PD, import matplotlib.py, plot as PLT. We're going to import a sub thing from, or yeah, matplotlib ticker called scalar formatter. That's a tongue twister, at least for me. Pandas. The one we might not have is Seaborn, but we can always install that quickly. I don't know if that actually got installed earlier. Oops. Shapely geometry, and then import earthpy as ET. SNS.set. So Seaborn is this nice kind of, I don't know, like newer version of PyPlot that simplifies certain tasks for you. I think a lot of people, or most people, still will use both, but actually, let's just try to import these and see if we have Seaborn. Okay, we do. Sick. Okay. SNS.set. SNS.set. I think the set might be deprecated, which is why it's getting slashed, but you can still use it. I think they're just letting us know that maybe you shouldn't use this forever. Let's just see if that works. Yeah, okay. So we're just setting the font and a style for the figures that we're going to create for the rest of this kind of notebook. And so it's nice kind of talking about how I didn't want to do templates in Google Slides. Seaborn creates templates that you can use for your figures, and it kind of just auto-magically renders in certain colors and certain styles, which is kind of nice. So let's set the working directory again and download the data. UIO home, Earth Analytics. Cool. Now let's load the shapefile using GeoPandas. So this is going to be the world boundaries. So OS jump path, join data. Spatial vector LiDAR global any 100 10 and any land.shp. And then let's read that in with GeoPandas. World bound path. And then let's show the first few lines of world bound. Cool. So let's actually plot this data now. We do 10 by 5. Bound dot plot. Let's make the color dark gray. Let's make the color purple. Purple's more fun. And let's set the axis to axis, AX. Next, let's set some labels on our axis object. So we'll set the X label equals longitude in degrees. Set the Y label equals latitude in degrees. And then let's set the title equals global map geographic coordinate system WGS datum or WGS 84 datum. This is a long one. Units. Oh, what does that even say? Units. Degrees. This is a long title. Okay, and now let's add the kind of gradicules, the grid that you see behind the data. So let's do AX. Set axis below true. AX y-axis grid color equals green. Line style equals dashed. Then ax dot x-axis dot grid. So you can see how it's kind of annoying if you have to do this every single time. But if you have like a script that you write that just runs all this logic, you can have hundreds or thousands of standardized figures created. Maybe not on hundreds of thousands of planets, but you know what I mean. If you have smaller data sites that you want to compare, it's kind of nice. Let's make them blue. Line style dashed. Let's see, let's show. So you can see we made a global map with some beautiful colors. You can see how we're already starting to level up our figure game. We're able to kind of specify styling on the actual vector data, but then also the kind of gradicules and other things. So this is kind of cool. I don't know how to do this in a desktop GIS software at this point. I'm sure it's possible, but I think it's at some point it gets easier when you learn these shortcuts. And this will become muscle memory after a certain point. The fig x equals blah, 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 how to plot things, and then how to set axes, labels, titles, all that stuff. It kind of becomes second nature the more you practice it, which is another reason why I'm kind of belaboring the point of typing this all out. So we have our global map data. Let's create some spatial point object data. So we're going to add 3 locations on the map. They're in decimal degrees. So let's create a point for Boulder, Colorado, Oslo, Norway, and Mallorca, Spain. Actually, let's do Boulder, Colorado, and then can we do Long Beach? And then let's do Joshua Tree National Park. So if someone could be awesome, could they look up the decimal or the latitude and longitude of Long Beach and then one of Joshua Tree and post it in chat, um, just so we can make it a slightly different graph. So I'm going to create a NumPy array to store those latitudes and longitudes. Cool. Thank you, Talissa and Viviana. So I'll copy the same one for Boulder. So it's negative 105.2519 and then 40.0274. Okay. So the next one we'll do Long Beach, which is negative 118. Negative 1937. And then it's like 33.770. Cool. And then finally for Joshua Tree, negative 115.9010. And then 33.8734. Thank you to those who posted this data in chat. It makes my life a lot easier. Now let's create a list of shapely geometries. And that's kind of a behind the scenes GIS library. And so we're going to convert these lists of numbers into actual point geometries now. And so we'll do that like this. City locations equals point XY for XY in add points. So this is a list comprehension type syntax where you're able to kind of loop over things inside of a list. And so you can now see we have 3 point geometries. Let's actually learn, or let's actually plot that data. So on top of the world map, big X equals PLT, subplots, big size 12, 8, world bound, plots, big size 10 by 5, color, K is another word for black. I forgot what it actually stands for. AX equals AX. City locations, plot, AX equals AX. Color equals spring green. Marker equals star. Marker size equals 45. And then let's set some labels. Longitude, degrees, Y label, latitude, degrees. Dude, I cheated in type to learn when I was a kid, so this is a struggle. I like chicken pick type my whole life, and working in tech, that's a bummer. It's a handicap. WGS 84 datum slash n. These are long. Units, degrees, latitude, longitude. Oof, almost there. AX dot set, axis below, true. X, y axis dot grid, color equals gray. AX dot x axis, grid, color equals gray. Line style equals dashed. PLT dot show. Who we got an error? City locations, blah, blah, blah. List object has no attribute plot. Ooh, do I have to convert it? Oh yeah, I have to, I skipped a step, my bad. I totally skipped the line without realizing it. So we have to convert city locations into a geodata frame. I totally skipped that. So GPD, geodata frame, city locations, columns. We just want the geometry column. And then we're going to set the coordinate reference system to the world bound CRS. So we can use the CRS from another data set to then set this one, which is kind of nice. And so then let's see. City locations should now be a geodata frame. Yes, it is. Now let's rerun this code. And you can see it's a little smushed because Long Beach and Joshua Tree are fairly close in the grand scheme of the planet. But all three of our data points have rendered. And you can see I have a typo here, which is fine. Now we're good. Cool. There's ways where you can zoom into the bounds of your underlying or of a specific data set, and we'll learn how to do that either today or sometime this semester. So you can kind of intelligently zoom in to where your data will just render nicely. And so you might be wondering, why are we doing all this kind of what feels like cartography with Python? I mean, it's because when you're doing analyses and kind of presenting your research or your work, you need to present it and be able to kind of nicely show your analysis. And so this is an important part of any kind of applied remote sensing project, is being able to display and communicate your findings. And visuals are often a really helpful aid in that communication. So now let's import some graticules and if anything, make this graph look a little worse in a way, but it's a helpful I guess, exercise. So let's import the proper graticules that can be projected into a particular coordinate reference system. So graticule path equals OS path join data spatial vector lidar global any 110 meter graticules all 10 meter graticules 15.shp. Now let's read in graticule into GeoPanda's data frame. Now let's create another geodata frame from a bounding box path. Data, spatial. So we're getting a lot of practice on importing data today, which is honestly not a bad thing. I'm not mad about it. Apologies for all the typing, but it's just part of it. And I strongly suggest typing instead of copy pasting because you do get muscle memory and it really does help you in the long term. Okay. Okay, so we read in that data. Now let's create the figure real quick. Big X. So you can see now we're being a little more explicit. We're specifying there's just going to be kind of one entry in our subplot. So fig size equals 15, 8. Let's plot the B box, the bounding box. Set the transparency to 10%. And then, or the opaqueness is, or it's 90% transparent. Yeah, I always forget how to phrase it. Okay. Color equals gray. Let's make it pink. It's a Barbie world. Okay, let's plot the graticule. Plot ax equals ax. Color equals. How about we make it purple? World bound dot plot x equals ax. Color equals. How about we make it red? And then let's plot our city locations on top of that. AX equals AX. Marker size equals 60. Color equals. Sure, let's do. Well, we make them black. Marker equals star. And then let's set the title and the axis labels. Next, that's set. World map. Blah, blah, blah. Next label, you can feel free to write blah, blah, blah too. I'm not gonna grade you on the correctness of that. Meters. Y label. Y coordinates. Meters. PLT.show. Nice. So you can see we have kind of a slightly chaotic map, but we're learning different ways to render data, reproject it, change the colors, do all that fun jazz. So now onto the good and the less good. So coordinate reference systems are in decimal degrees are helpful when you need to locate places on Earth, but it's not using a uniform measurement unit. And so it's not really useful for measuring distances. And so that's why other coordinate reference systems have been developed. And so let's look at some of these projected coordinate reference systems. Sorry in advance if you hear my stomach rumbling. Did not eat before class. Cry. So let's now use the Robinson projection and have some fun with this. So let's specify a projection of Robinson. And then let's do the Robinson graticule as well. Equals graticule dot to CRS plus. So you can see we have this existing data, the world boundaries and the graticules, and we're just projecting it using this, or reprojecting it using this toCRS method, and then specifying the projection that we want. That's pretty simple in my book. I'm a fan. So now we have this projected data in our Robinson projection. Now let's actually plot this with Python. So again, figx blt.subplots, big size equals 12, 8. Let's do world bound robin.plot ax equals ax, color equals spring green. Now let's do graticule robin plot ax equals ax, color equals let's make it blue. Okay. Now let's set some titles. ax.set title equals world map Robinson. X label equals X chords meters. Y label equals Y chords meters. And then for axis and AX in, let's do a list. AX, so this is like a for loop now. So for the axes in the x-axis and the y-axis, let's do some stuff. Namely, let's use the scalar formatter to format that data. It's scalar formatter. And we're going to set so that it is not scientific data. Like scientific notation of the numbers, so they're a little easier to read. And then axis.set major formatter. And so you can see we have our beautiful, beautiful figure. But yeah, if you spend more time and tweaked it to your liking, you could definitely make this more interesting and usable. But really, we're just kind of getting the building blocks of how to make maps and visualize vector data today. So what happens if we add the same latitude and longitude locations to our map? So we'll see that there's not really on-the-fly projection. And for this case, I will just copy paste it, so you don't have to see me do that again. But I will add a new entry here for city locations. And let's use a star marker again. Size equals 100 and color equals, let's make it black so it's easy to stand out. Nothing else has to change. Actually, we'll add one more line here. PLT axis equal, and then let's do a PLT.show. And so you can see that our data is not really rendering anywhere where it should be. Like none of our cities are in, this is like south of Ivory Coast, south of like Ghana. None of the countries were picked were in West Africa. So we need to project our data. So let's do that real quick. Let's reproject our point locations to Robinson projection and see what that looks like. Equal city locations, CRS, world bound, Robin, CRS. And then I'm going to not practice what I preach and do some copy pasting. And we're going to change city locations to city locations Robin. Everything else should be fine. Now these should render where we expect. And you can see I spelled world bound Robins incorrectly, which is fine. And now our cities are rendering where we actually expect in Boulder, Long Beach, and Joshua Tree. Super cool, or kind of cool. Okay, next let's compare two maps. I think this will be the last part of this mini lab. So they look visually different in these different coordinate systems, but let's actually look at them side by side. So let's go Reticule Robinson. Sponge equals Robin. ebox.toCRS plus proj equals Robin. So let's do fig. And then we're going to have two axes now instead of one. AX0 and AX1 equals plt.subplots 2, 1, fig size equals 13 by 12. Now let's work on our first plot. Plot 1. bbox.plot ax equals ax0, alpha equals 0.1, color equals gray. Radicule.plot ax equals ax0, color equals light gray. And then world bound.plot ax equals ax0. Might see a pattern at this point. Color equals black. City locations. Plot ax equals ax0. Marker side equals 100. Spring green. X0 dots set title equals world map geographic long flat degrees. Now let's do the plot number 2. I'm going to copy a lot of those. Basically this whole chunk and then just tweak it line by line. So bbox Robinson, basically adding a Robinson. So I'm going to highlight and copy this underscore Robinson just to make my life a little easier. Radicule Robinson. And this one's actually Robin. And then this one's actually Robin. And then I got to change all the AXs to 1. including this one. And then this is world map. Projected Robinson meters. And then one last section. Axis in AX1 x-axis, AX1 dot y-axis. Actually gonna copy that from here. Then let's do a plt.show. It's thinking. And so you can see we have two figures. Geographic latitude and longitude, and then projected. And so this is an example too, where we're having multiple subplots in a single figure. So that's really it for intro to CRS. I'm gonna save these changes and then jump into the next one. So finish lesson 2. That's thinking. Okay, it's done. Now let's return, just double check that our GitHub repo is updated. Great. Okay. Next, let's jump into geographic versus projected coordinates reference systems. So I'm going to create another notebook here. Let's do touch geo versus proj.ipynb. Let's open up this lesson right here, have a look. So we previously explored the basic concepts of the coordinates reference system. We looked at geographic coordinate systems and projected coordinate systems. Now we're going to learn a little bit more about those in detail. So there's not a single CRS that's the best for everything. It's really just there's trade-offs that you have to consider. So I'm not sure this one has a ton of code, to be honest, this lesson, but we'll find out shortly. So geographic coordinate systems are often, but not always, in decimal degree units. And they're great for when you need to locate places on Earth, like the planet, like global maps, but they're not ideal for measuring kind of uniform distances. So they're not great for like getting from point A to point B and measuring how far that'll be. I guess there is some code. Cool. So let's dive into the structure of a coordinates reference system. So it wraps around the entire globe. So each point on the globe is defined using the same system and the same units. But it's important to remember distance is distorted. And there's an origin at 0.00 located at the intersection of the equator and the prime meridian. So let's jump in and get some more practice. So let's select the Python 3.10.13 kernel and jump in. Import OS from glob, import glob. The one you might not be familiar with is glob. It's a way to kind of list, like, you can filter for files that match a certain pattern using glob, filter for things based on kind of yeah, really just like a pattern. And I think we'll see in this lesson an instance of that. Um, Importing a lot of familiar faces. Picker, import scalar formatter, import pandas as GPT, from shapely dot geometry, import point, import earthby as ET, import seaborn as SNS. Let's set the font scale 1.5. Let's set the style white. Data equals ET data get data spatial vector lidar OS shadir path join etio dot home earth analytics. There should be good. Boom. Matplot. That's why matplotlib. Cool. Now let's jump in. Actually, we're not starting with code yet. Okay, I'll go back to the Colorado resource. So they're just showing this kind of map that we kind of messed with in the previous lesson. Projected coordinate systems. They are used for more accurately capturing distance, shape, and or area. Okay. So it's just mathematical calculations performed to flatten the 3D data onto a 2D plane. So this kind of globe into some kind of flat representation. Some areas are stretched, some are compressed, and you can see the distortion when you look at the map of the entire globe. So a common one that you'll hear about is UTM, Universal Transverse Mercator. The whole globe is divided into UTM zones. I think we're in UTM zone 11 North in California. Different places have different zones. But each kind of zone has its own projection that's optimized for that region. So the origin for each UTM zone changes and it's intersected or it's located at that intersection of the equator and the location 500,000 meters east of the central meridian of each zone. It seems kind of arbitrary, but I think there's been a lot of math and thought put into that. Cool. So you can see here an example of the UTM grid. Yeah, we're around this general area in California. So like, yeah, 11-ish, I think. So let's actually get some experience with UTM in Python. So let's create a data frame for the Boulder or the city of Boulder and plot it. So we'll do Boulder df equals np.array 476911.31 and then 4429455.35. Cool. Geometry equals points xy for xy in Boulder df. And then Boulder lock equals GPD geodata frame geometry columns equals geometry CRS equals at EPSG 2957. Okay, so ignoring that, it's just some kind of deprecated method, not really of a concern for this lab. Now let's actually plot that information. So we'll do fig x equals plt subplots, fig size equals 10 by 10, boulder lock dot plot, ax equals ax dot set title plot of boulder CO location. Let's do a plt dot tick label format use offset equals false, and then a plt dot show, and we'll see a really ugly figure. Okay, so I didn't. That's why. PLT dot subplots. Great. Super ugly. Let's try to make it nicer. Well, first, let's get some information about the coordinates reference system. Boulder boulder block.crs. So you can see it's in UTM zone 13 north, which makes sense, I think. Colorado is a bit east of us. So 13 is east of 11. Just information about areas of use. Canada, Northwest Territories, Nunavut, Saskatchewan. That probably lines up with Boulder. Now let's reproject that data into the geographic coordinates reference system. And then we'll notice how the coordinates are different, but represent the same location. So we'll do Boulder df geog equals Boulder lock to CRS EPSG equals 4326. And then we'll do a Boulder df geog.crs. And now you can see that it's representing the same area, but using entirely different units, slightly different information displayed because the geographic coordinate system is global. They're not going to say that it's used for specific parts of Canada or whatever. It's like the whole globe. So just something to note. And then let's actually plot our data in the map. So we'll do fig x equals plots. Fig size equals 10 by 5. World bound dot plot. CMAP equals grays. AX dot set. Title equals Boulder CO world map WGS 84. Then we'll say X label equals X. Or we'll just say des X in decimal degrees. I don't feel like typing it. Oops. Went a little early. Okay. Y label equals Y in decimal degrees. Boulder df geog.plot. AX equals AX. Marker size equals 52. Color equals spring green. plt.show. Okay, world bound is not defined. Good to know. I just need to import that. Interesting. So they just assume we have it from the last lesson, which is a bummer. Okay. Let me read that in real fast. Let me see. We had it here somewhere. World bound. There we go. Let's read that in here. Okay. Now let's try this again. And you can see that we have our map with Boulder displayed. Very cool. Nothing, I mean, it's not that cool. We're just kind of transforming between a projected coordinate system and a geographic coordinate system. So it's kind of boring. But to me, I view this as all muscle memory. We're getting practice in using Python, plotting things, accessing geodata frames, doing common operations on them. That's really what, for me, today is about getting your sea legs, getting comfortable doing these sorts of things. So we can do more advanced, interesting things in the coming weeks. That's it for this mini lesson. So let's commit our changes and continue. Okay, so save this, commit and sync. And before we continue on to the next lesson, I'm going to run to my kitchen and get a refill of coffee. And so I encourage you all to do the same. Staying caffeinated is very important. Unless you have an aversion to caffeine, which then feel free to stay uncaffeinated. But it's a Saturday morning and we're working, so I think caffeine is kind of required. Okay, so we finished this lesson. Let's double check that our GitHub is reflecting that change. Cool. I'll be back in like 60 seconds or less. Feel free to talk amongst yourselves briefly, but I need a refill. So I'll be right back. I'm back. Okay. Let's continue. So now we're going to jump into understanding EPSG, WKT, and other coordinate reference system definition styles. So I'm going to create another notebook. Again, I don't know how much this lesson will entail in terms of code, but it's always good to just create a notebook. So we got 3.10.13 Python kernel. Good to go. Let's understand. So we've previously dived into the basics of CRS, what CRS entail, the different kind of components, and how to convert between projected and geographic CRS. Now let's learn about kind of the formats that coordinates reference systems are stored. We encountered a few actually in the previous lessons without really calling it out, but some common formats that you'll encounter are the proj4 format, EPSG, and well-known text WKT formats. And so spatialreference.org is a super useful website that can show you kind of all these different formats for a particular data set, and kind of interconverting between them and which ones you need. So to start, let's jump into the proj4 strings. They're compact, useful way to identify coordinate reference systems. GeoPandas can natively accept them. However, there are many libraries are moving away from proj4 to an even more concise EPSG format. So you can see how certain proj formats are a little verbose. Proj4 string, that's a lot. Whereas in EPSG, you could just specify a 4 or 5 code number and say all that same information. And so that's one of the reasons why proj4 is not particularly in vogue as much anymore. Secondly, we can pivot to the geographic proj4 string. Again, it's pretty verbose. It makes sense, like longitude, latitude, datum, the ellipsis, which is kind of I think that's the definition of the Earth. Yeah, the ellipsoid shape of the Earth. But you can see how this is it's a lot of information that you can mess up when you're specifying. And so if there was an easier, more concise representation of the same thing, that would be super useful. So let's now pivot to EPSG. So there are 4 or 5 digit numbers that represent these CRS definitions. And the EPSG acronym comes from the European Petroleum Survey Group. A lot of GIS innovation has come from kind of mining and petroleum type things where industry needs a way, and academia and governments need a way to, I guess, model the earth for the sake of inventorying how many natural resources are there. And so you'll see a lot of this type of work from petroleum and mining. So let's get some quick practice with EPSG. To start, let's import all our familiar faces. Oops, matplotlib.pyplot as PLT. Shapely.geometry. Import points. Import earth as ET. And then let's set the working directory and get the data. Earth analytics. Cool. Let's import the world boundary shapefile and output the coordinates reference system as a quick reminder, as if we didn't just do that for the last 30 minutes. OS path. Global. Globale. Any one land. Ah, struggling. World bound equals GPD read file. World bound path. And then world bound .crs. Cool. WGS 84. So the CRS consists of two parts. The init, which tells Python that a CRS definition will be provided, and then the EPSG code itself, EPSG 4326. Cool. So how do we create a CRS object in Python? So often we'll have to define the CRS for a spatial object. Like previously, we created new points and had to define the CRS. You can manually create an array for a single point and turn that into a shapely object and convert that into a GeoD or a GeoPandas geodata frame. And we did that previously. And so let's quickly do that again for the city of Boulder. Boulder XY equals np.array 476.911.31 and then 4429455.35. Boulder XY point equals point XY for XY in Boulder XY. Now let's do Boulder block equals GPD geo data frame Boulder XY PT columns equals geometry CRS equals init EPSG 2957. Block.crs. So ignore that future init warning. And we can see that we have a typo here because I forgot to use curly brackets. It's supposed to use those instead of square brackets. Let me fix that mistake. And then let's double check where I messed up. Missing a square bracket here. Should remove this square bracket here. Now I expect it to work, and it does. Cool. So we have information about this data set. So it's useful to recognize this format, the WKT. Esri uses this often, so does Envy. A lot of desktop GIS software use the WKT well-known format, well-known text format. So let's just acknowledge that. I don't know that we're going to actually use any code with WKT, but if you wanted to, you could convert to WKT. That's actually it for this lesson. So we can now save our changes and continue. So let's commit and sync. What lesson is this for? Okay. we're getting there. I think we should be done by like 12:30. I don't imagine it's going to take the full time today, even though there's 9. Some of them are a little shorter. Okay, so it's done. Close this. We can double check that our lab 2 has our EPSG notebook, and it does. Awesome. Now let's move on to reproject vector data. So I'm going to create a new notebook. Open it with the Python 3.10.13 kernel, and then we're good to go. So we've been kind of dancing around coordinate reference systems a lot today, so let's just continue that dance. Oftentimes you're going to kind of have data from multiple different sources with different coordinate reference systems. And so I think we're going to, in this lesson, learn tips and tricks on how to interconvert for the sake of analyzing disparate data sources. So you might get data in different CRSs because the data is stored in a particular CRS convention by a particular data provider, such as like a federal agency or state planning office. You might also receive custom or a particular CRS for customized to a region, like state plane is particular to like California or Nebraska. And so there's a plethora of reasons why you might have to interconvert or transform the projection of a data set into another for the sake of an analysis. So let's jump right in. Going to import OS, import NumPy as NP, import matplotlib pyplot as PLT, import Seaborn as SNS, import GeoPandas as GPD, import EarthPy as ET. Awesome. Let's set the Seaborn style to white. We're going to set the font scale to 1.5. And then let's set the working directory and get our data. Get data, spatial, vector, LiDAR, and then os.shatir, os path, join, etio, home, Earth, analytics. Awesome. Okay. So let's go in. Let's plot the roads data. Apparently this was a challenge in a previous lesson that we skipped, but that's fine because we'll just do it now. So let's get the San Joaquin experimental range roads data and area of interest boundary. And then let's get the coordinates reference system of them. So to start, SJER roads path equals OS path join data spatial vector LiDAR California Madera County roads TL 2013 06039 roads.shp. Let's now read that into a geodata frame using GeoPandas. Now let's do a similar thing for the area of interest boundary. SJRAOI path equals OS path join data spatial vector LiDAR. And the reason we're using OS path join and not just hard coding the path is because OS path join allows you to be operating operating system neutral, so you don't have to worry about Mac versus Windows path names. It just magically handles it for you, which is pretty nice. Why? Let's create a geodata frame. And then let's print out the coordinates reference systems for both of those geodata frames. So you can see the roads is a 4269 EPSG, and the area of interest is a 32611. So they do not line up. So we need to change the CRS of one of them. So let's change this data. Let's reproject the area of interest. So here's a note from the authors. When you reproject data, you are modifying. Thus, you are introducing uncertainty into your data. Slightly less important at this point, but it's something to consider. And so you may want to consider keeping the data that you're doing the analysis on in the correct projection. And so in this case, that would be perhaps the roads instead of the AOI. And so if you're simply reprojecting to create a base map, it doesn't really matter. So for this case, let's reproject the area of interest boundary. We'll do SJER, AOI, WGS, 84. And let's do SJER, AOI to CRS, EPSG equals 4269. Voila. Now let's plot our data together because they're both in that 4269 projection. Fig X equals PLT subplots. Fig size equals 12 by 8. SJER roads dot plot. AX equals AX. Alpha equals 0.5. CMAP equals grays. SJER AOI. WGS 84. Plot AX equals AX. Marker size equals 10. Color equals red or R. And then AX dot set title Madera County roads with SJER AOI PLT dot show. Oops. So I got a typo there. Instead of an equals, I have a minus. No worries. Voila. You got our roads, got our area of interest. Wonderful. Now let's try this process again, but let's use some census boundaries. So we're going to import some census data, some US census data with boundaries of continental states of the US. Cool. So let's read in that data. State boundary US path equals OS path join data spatial effect door LiDAR USA states census 2014.shp state boundary US equals GPD read file state boundary US path. And now let's output the type of this data. It should be a geodata frame. And now let's output the head. So you can see we have information about bound. So District of Columbia is not a state, but for the sake of this, it's basically a state. California, Florida, blah, blah, blah. These are the first 5 in the list. With a bunch of relevant attributes like the state code 06 for California, name of the state, area land, area water, what geographic region of the US it's in. So now let's plot this data. So we'll do fig x equals PLT subplots. Fig size equals 12 by 8. State boundary US plot AX equals AX. Base color equals pink. Edge color equals green. AX dot set title equals map of continental US state boundaries. United States Census Bureau data. ELT.axis equal AX dot set axis off. ELT dot show. Nice. Pink and green US. So now let's, you can add a boundary layer of the US to make it look nicer. And if we specify a thicker line, it'll make our map visually pop. Let's try that. County boundary US path equals OS join. Join. Data. Spatial vector LiDAR. Oops. USA. USA boundary dissolve dot shape. Down T bound. Spelling, man. County boundary US equals GPD read file county boundary US type county boundary US should be a geodata frame, and it is. Now let's plot it. So fig x equals plt dot subplots fig size equals 12 by 7. County boundary US. Oh, it's country. Okay. That's why it didn't make sense to me. Country. There we go. US. I really do need to get glasses. The universe has been telling me lately. That it's going to be obnoxious. Line with equals 1. AX dot set axis off. PLT dot show. Interesting. So we have an error. I spelled something wrong. Line width. There we go. So we can see our outline of our whole country in purple, but then our states within. So yeah, it pops a little better. So let's add our San Joaquin experimental range site locations to our map. So we'll do fig x equals plt dot subplots. Fig size equals 6 by 6. SJER AOI dot plot. AX equals X, color equals indigo. Let's just do AX dot set. Title equals SJER AOI. AX dot set axis off. ELT dot show. So that's our area of interest. Let's actually plot it on a map now. Okay. Let's add it to our US map. Fig x equals PLT subplots. Fig size equals 6 by 6. Country boundary US dot plot. AX equals AX. Edge color equals black. Color equals white. Line width equals 3. Alpha equals 0.8. State boundary US dot plot. AX equals AX. Edge color equals gray. Color equals white. SJER AOI dot plot. AX equals AX. Color equals indigo. AX dot set axis off. You can see it's not great. So we're missing, we got an error, which is cool. So I think I wrote PLTS somewhere. Yeah. So let's try that again. You can see it's kind of an ugly graph. Like it's not great. So let's check the CRS of our data sets to make sure that we're doing something correctly or that we're doing something wrong. Print SJAR AOI CRS. Country boundary dot US.CRS. Print date boundary US.CRS. So you can see we need to reproject our San Joaquin experimental range AOI. Cool. So it seems that our data are in different CRS. We should reproject them in order to display them on the same map. I see it's Alyssa. Cool. Now let's view the spatial extent of both of these data sets before we reproject them, just out of curiosity. So let's print SJER AOI total bounds. Let's also print state boundary US total bounds. So you can see they're entirely different units. Latitude and longitude versus decimal degrees. So let's now reproject our San Joaquin AOI data. and we're going to convert it to the state boundary US CRS. And then let's print out the CRS info of the newly reprojected data. SJER AOI WGS 84 dot CRS, and then print state boundary US dot CRS. Okay, cool. So we notice our total bounds are now on the same units as the state boundary, which is cool. Oops, printing out the wrong one. Now you notice that these units match the state boundary US units because they're in the same projection. This is actually a typo right here. So you could also use the full proj for string, but that's kind of annoying. As you can see, it's just it's super verbose. So using something like the CRS or EPSG it's preferred in my opinion. So now let's try to plot again all the data. Hopefully it works. Twelve by 8. Actually, I'm gonna copy this. I'm gonna be bad. Country boundary. Let's just follow the same order that they have. So state boundary AX equals AX, line width equals 1. Edge color is black. And then we won't specify inside color. Country brown or boundary. Let's do AX equals AX. Alpha is 5 or 0.5. Edge color black, color white, line with 3. Okay, now SJER, AOI, WGS 84 dot plot, AX equals AX. Color equals whatever, indigo is fine. And then edge color equals R. Now let's do AX dot set title. AX dot set title equals, oops, map of continental US state boundaries /n with SJERAOI. Nice. And you can see our SJERAOI is really small and in kind of central California. So now let's actually try to improve our figure a little better with some zooming. Like I alluded to before, you can kind of intelligently zoom into features using Python. So let's try that out right now. I'm gonna actually copy a lot of the same thing here, just to show you that it's very similar. And we just have to add one line. So we'll do AX.set xlim equals -125, -116. And so here you can see we're hard coding the limits or the boundaries, but there's ways to automate this that are pretty cool. But for the sake of this, it's fine to just hard code it in. And so now you can see map of continental US state boundaries with SJER AOI. We're zooming in a little bit better to our study site of interest. Unfortunately, it's still a little small. The AOI boundary is a polygon, and it's just a little too small to see on the map. So let's convert that polygon to a centroid and then plot it again. And that'll be nice. So let's quickly create a centroid. AOI point equals SJER AOI WGS 84 geometry dot centroid. Cool. Now let's plot this. So you can do, who did I spell it? AOI point. Okay. I'm going to take this whole thing and then we're going to replace this with SJER or with AOI point. Plot. You want to do a marker size 80, color indigo, and let's do a marker of a star. A little better. So you can see how we're kind of improving. We could similarly do this without boundaries, and we'd have the full extent of the US. So now our data lines up on our map, which is kind of cool. Okay, that was it for this lesson. Let's save our results. Commit changes to our repo and continue on. It's thinking. There, it's done. Cool. Can go back here. I always just like to double check that everything is loaded. Reproject exists. Awesome. Cool. Now let's create a notebook called Clip Vector and get some experience clipping spatial vector layers in Python. Again, we're going to select the Python 3.10.13 kernel and jump right into it. So how do you clip vector data in Python? Or I guess first is, what is clipping? It's when you kind of remove data outside of an area of interest or an extent that doesn't matter to you. And so your clip data set will be smaller than your original data set. And so data from your original data set will be cut based on the boundaries of some kind of clip object, like a cookie cutter. And so in this example, you can see there's points, there's some lines, there's polygons. You could overlay something and cut out kind of a subset of that chunk. And when would you want to clip data? Perhaps you have more data than you need. So clipping outside of your study area to reduce processing, just easier to manage. This just simplifies a lot of statistics and just removing information that might not be relevant to your research. And then also when you're plotting data, you might only want to clip your data to show just a subset of sites of interest. And so now let's learn how to crop our data and zoom in on extents a little more using some familiar libraries. So let's import the usual suspects. OS, numpy, lib.pyplot. SPLT. A new one, matplotlib.lines. Also another one, listed color map. Import GeoPandas as GPD. From Shapely dot geometry, import box, import earth as ET, import seaborn as SNS, import warnings, import warnings dot filter, ignore geoseries dot not na user warning. It's just basically ignore some warnings about missing data. We'll learn how to handle missing data a bit later today. Font scale equals 1.5. Let's set it to the white style. And then let's set our working directory and get our data. Data, get data, spatial vector, LiDAR. OS, Shadir, OS path, join, ETIO, Earth, analytics. Got a typo. Should remove that. There we go. So let's clip a shapefile in Python. So we've been dealing with a country boundary for the US, state boundary layers for the US, and populated places. And so let's do some clipping. Let's clip the points that we need for our project, namely the points that overlay on top of the continental US. So let's import some data and get started. Country boundary US path, US path, join data. Vector, LiDAR, USA. SHP. Let's read it into GeoPandas as a geodata frame. Let's do the same thing for the state boundaries and for populated places data set. Spatial LiDAR, USA, states, 14.shp. Read it in GeoPandas as a geodata frame. Do the same thing for populated places. Global, any. Needed places, simple. Any 110. What does it actually say? And then let's read that in with GeoPandas. And then let's check that all the data are in the same coordinate reference system. So we'll do that right here. and rinse up places. Cool. Same coordinate reference systems. So let's plot the data. Size equals 12 by 8. So let's do country boundary US dot plot AX equals AX, alpha equals 0.5. State boundary US dot plot AX equals AX, alpha equals 0.5. CMAP equals grays up places dot plot AX equals AX. And then we'll do PLT axis equal AX dot set axis off and a PLT dot show. Nice. So you can see we have our US boundaries and a ton of locations that fall outside of the continental US. So let's jump into clipping. So we're going to use GeoPandas to start. And so we're going to use the clip method. So let's try that. We'll do points clip equals gpd.clip populated or pop places, and we're going to use the country boundary as the clipping layer. So then let's display the first 6 rows and a few of the columns of these populated places. Let's clip, name, geometry, scale rank, mat scale, dot head. So you can see we have cities like San Francisco or Miami, Houston, Atlanta, Los Angeles, San Francisco. Now let's plot the data using this newly clipped points layer. All right, let's get it. There you go. It's equals PLT dot sub plots. Big size equals 12 by 8. Country boundary US dot plot AX equals AX. Alpha equals 1. Color equals pink. Edge color equals red. State boundary US dot plot AX equals AX. Alpha equals 0.5. CMAP equals purples. Points clip dot plot AX equals AX. Column equals name. Now let's turn off the axes for the ticks. Set them to be equal. And then let's label the points. Actually, let's do it without labeling, and then we'll do it with labeling. Oh, so we got an error because I spelled something wrong. What? So you can see we have our points, our layers, some chaotic colors. Now let's add in some nicer labels, actually. So I'm going to use the same underlying code, but then add in one extra bit of logic. So we'll do points clip dot apply, and we're using something called the lambda function, which is like a function without creating a whole function. Don't really need to worry about it now, but it's just a way to do things a little more shorthand. And so we're going to label the points clipped layer using some attributes contained within the geodata frame. So xy equals x dot geometry chords 0. XY text equals 6, 6. Text chords equals offset points. Background color equals green. And then axis equals 1. So it's thinking, ooh, we got an error. Cool, cool. Let's see where I messed up. Missing one positional requirement. Text. Okay. Let's see if I just misspelled something. Points clip apply. Lambda x. Ex dot annotate s equals x name. Okay. Ah. xy x dot geometry dot chord 0. xy text 6, 6. Text chords offset points. Background color. Okay. Let's try again. Weird. Okay, let me try. Let's see if I'm just typing something wrong. And if not, we'll just continue and not worry about labeling. Interesting. Okay, yeah, so I think that there might just be something broken with this labeling logic. Don't worry about it. I'm just going to totally ignore it. And we're good. So now you can still see we were able to clip the data effectively. The labeling is kind of just extra credit flavor. So let's clip a line or a polygon layer to an extent. So we started with points. Now let's move on to more complex vectors. So let's clip the roads layer. So we're going to use the country boundary layer and a clipped version of the natural earth 10-meter roads layer. And so let's try to do this. So roads path equals OS path join. And E10 and 10M roads. Okay, any roads equals GPD read file, any roads path. But similarly, or now let's check if our roads and country boundary layer are in the same CRS. So we can do that like this. If any roads dot CRS equals both layers are in the same CRS, else. Both layers are in the same CRS. Nice. So now let's clip lines and polygons. So let's clip the data. I'm going to skip the simplification code that like simplifies the boundaries. So we'll see how long it takes without simplified boundaries. Any roads clip equals gpd.clip. Any roads, country boundary, US. Any roads clip. Any roads clip. And we're going to ignore missing and empty geometries. So now print the clipped data have fewer line objects. Any roads clip shape. Any roads shape. So it's going to take a moment. It's thinking. It's a fairly large data set. And I spelled something wrong, which is fine. Try it again. So you can see that the original data set had 56,000 entries, whereas the newly clipped data set has 7,300, which is much less. Now let's plot the data. Fig AX1, AX2 equals plt.subplots. 2, 1, fig size equals 10 by 10. Any roads dot plot AX equals AX1. Any roads clip dot plot AX equals AX2. AX1 dot set title on clipped roads. AX2 dot set title clipped roads. AX1 dot set axis off. AX2 dot set axis off. ELT dot axis full. ELT dot show. And soon you'll be able to see our unclipped roads for the whole planet, and then our clipped roads for the continental United States. Now let's plot the cropped roads on top of the continental boundaries. Each color equals blue. Alpha equals 1. Any roads clip plot AX equals AX, color equals so let's do purple. Set axis off. ELT.axis equal ELT dot show. Look at that beautiful graph. Beautiful. But yeah, you can see that we're getting some experience clipping and displaying that clipped data. And you can notice there's no roads outside of our clipped boundaries, which is quite nice. If you really wanted to, we could have simplified the data And let me quickly show you what that simplified data actually looks like. Um, so we'll do country, boundary, US simplified equals country, boundary US dot simplify. 2, preserve topology equals true. And now let's plot this. See, I spelled things wrong. Boundary. So I didn't actually plot it. Let's plot it now. And you can see it's kind of a simplified version of what we were dealing with before. If you increase the tolerance of simplify, I think you can create a more aggressively smoothed map. So you can see how it's kind of smoothing out. If I set it to 9.9, we have a pretty rounded simplification. So now let's do a nice, pretty map with some more colors of the categories of roads in the US. So we'll do big X equals PLT dot subplots 12 by 8. Country boundary US dot plot AX equals AX, alpha equals 1, color equals black, edge color equals looking black. Now let's do any roads clip plot AX equals AX, column equals type, legend equals true, AX dot set axis off, BLT dot axis equal, BLT dot show. Gorgeous. You can see we're making cooler and cooler maps by the minute using Python. This is mainly vector data, but you can see how in the future, when we have maybe an image, we can lay vector data on top of imagery to kind of display information about a study site. Cool. Let's now try one last fancy map and try to do, depending on the road type, the thickness will vary. Let's see if this works. So let's do custom legend. So we'll do road attributes equals, this I will copy paste. I will mess that up so fast. Okay. Big X equals PLT dot subplots. Big size equals 12 by 8. For C type data in any roads clip dot group by type. Data dot plot color equals road atters C type 0 label. Actually, this should be here. Line width equals road atters C type 1. Okay, now I know why it was giving me grief. There we go. Okay. Country. Boundary US dot plot. Alpha equals 1. Color equals edge color equals purple. AX equals AX. AX dot legend. Frame on equals false. Block equals 0.1. Negative 0.1. That's just telling where the legend should appear on the map using kind of map units, not anything to do with latitude or longitude, but just kind of like figure units. Set title, United States, roads by type. Font size equals 25. AX.set axis off. PLT.axis equal. PLT.show. Oop, got a typo. Jada. Interesting. There we go. Nice. So miss another typo here. There we go. So you can see we've created a map, roads by type, nice legend, some colors. You can see the thicker ones are beltways and kind of going to smaller and smaller type roads. That's it for this lesson. Let's save our changes, keep going, push through, try to get done in the next half hour or so. Okay, finish this one. Let's just double check GitHub looks good. Reproject. Yeah, or clip vector. Yes. Okay. Now let's do dissolve polygons. Touch. Let's open that, select the 3.10.13 Python kernel, and just jump right in. This one should be a shorter one. And we're just jumping right into dissolve. Let's go. Okay. No hesitation. So let's import the libraries we'll need. Import OS, import numpy as a key, format at plotlib dot py plot as plt. Lib dot colors, imports listed color map. Port Seaborn as SMS. From shapely dot geometry. Import box. Import GeoPandas as GPD, import Earth I as ET, SNS.set, font scale equal 1.5, SNS.set, style. Let's try dark. I think dark is an option. Let's see if that works. Matplotlib colors. No module shapely geometry spelling. Okay. Data equals ET. Data get data spatial vector lidar. os.shadir os path join ET.io home Earth analytics. Now let's import the data. Base path equals os path join data spatial vector lidar. Boundary path equals os.path join. So you can nest os path join inside of another os path join, which is kind of cool. Base path USA boundary dissolved .shp state boundary path equals os path join base path USA states census 2014 and then pop places path equals os path join base path global any 110-meter populated places simple. Any 110 rated places simple to SHP. And now let's import the data with GeoPandas. Equals GPD read file. And pop places equals cool. Got an error. Country boundary path. I spelled it wrong. Country. There we go. So let's dissolve polygons based on an attribute. So let's dissolve the US states by region. So we saw regions like west, northeast, south. Let's take a look at those again. State boundary, US.head. So you can see we have a list of states, and then the region is a categorical label applied to them. So let's dissolve based off of region. So we'll do that. State boundary equals state boundary US. And just these two columns, geometry. Now, continental USA equals state boundary dot dissolve by equals LSAD, which is this kind of blank column here. Let's see what happens when we try that. Quant USA. So a single multi-polygon entry. So let's try to plot this. X equals plt.sub plots big size equals 10 by 6. Cont USA equals, or no, cont USA dot reset index dot plot column equals LSAD, AX equals AX dot set axis off. Excuse me. Ooh, excuse me. Okay, AX or PLT dot axis equal PLT dot show. Okay, that's not super exciting. Let's actually dissolve on the region boundaries and not just the whole country. So we dissolve the state level polygons globally. So let's now try a better way. State boundary equals state boundary US region geometry area land area water. Now let's summarize the quantitative columns by sum. So we'll get the sum of land and sum of water across these regions. Regions ag equals state boundary dot dissolve by equals region. Ag function is sum. Now let's get regions ag. So you can see we have now the data set in 5 records instead of all 50 because there's 5 regions of this country in this data set. Now let's try, or at least in these first 5 records, now let's display some more information. So we want to convert the units from square meters to hectares. So let's do that with a little math on our data. So we'll do regions ag, land in hectares equals regions ag area land divided by 10,000. Similarly, we'll do regions ag water HA with a similar conversion. And you'll see we have 2 new columns. Now let's plot this data, and then we'll be done with this lesson. Okay, fig AX1, AX2 equals PLT dot subplots 2, 1. Fig size equals 10 by 10. Regions ag dot plot column equals land HA legend equals true scheme equals quantiles AX equals AX1. Now let's do regions ag dot plot column equals water, H A legend equals true, scheme equals quantiles, AX equals AX2. Now let's do a super title above the plots, the subtitle, census data, total land and water by region, hectares, font size equals, what is the font size? 16. Let's make it a little bigger. Let's make it 20. Okay, now let's do ledge equals ax1 dot get legend. And now let's set the bounding box to anchor the legend in a specific location in our figure. Let's do the same thing for the secondary legend. Leg equals ax 2 dot get legend. Leg dot set bbox to anchor 1.51. ax1 dot set axis off, ax2 dot set off, blt dot axis equal blt dot show. Ooh, mess something up. Okay. Spell something wrong. Oh, scheme keyword. Nice. See if I messed up somewhere. PLT sublab, land HA, scheme, quantiles, AX equals AX1. Interesting. Trying to figure out where the error is. Seems like it doesn't like this first line. The map classify package is required to use the scheme keyword. So it seems like I need to import map classify. Let's try that real quick. I think that's why it's not working. So let's do a pip install map classify. Now let's try this again. Nice. So you can see the top one, this is land, and the bottom one is water. And it shows kind of the regions by area by land. It seems like the West has the most area by land, whereas area by water, it would appear that the Midwest region wins there. And if anything, the West has decent amount of water too. Okay, but the South does not as much. That's it for this slab. Let's save these changes and push on. $12.30 might be a little what's the word? Unrealistic, but not too much long after that, I think. We can blast through the next ones pretty quick. Okay. Make sure everything is in our GitHub repo. Yep. Now, okay, cool. Let's create a new notebook called Join Attributes. Nice. And then there's 5 of us here, including me. Cool. We got this. Touch, join attributes. Select the Python 3.10.13 kernel. And let's get started. Oh, this is a short one. Sick. Right into code. Let's do it. Import the usual suspects. Import OS, import map. See. Imports listed color map. From shapely.geometry, import box, import geopandas as GPT, import earth pi as ET, data equals ET dot data, get data, spatial vector lidar, OS Tradir, OS path, join, ETIO, home, earth, analytics. Okay. Let's import our data. Data path equals OS path join data slash spatial data show vector lidar. Now let's do country bound US equals GPD dot read file OS path. You can see how we're kind of nesting things now. Data path USA USA boundary dissolve.shp state bound US equals similarly gpd.read file os.path join data path USA USA states census 2014 dot sheep up places equals gpd read file os.path dot join data path global any oops populated places simple.shp. Okay, and then any roads equals gpd file os path join data path global any tenem roads any tenem roads dot shp. Cool. Got all our data. OS has no attribute path underscore join. That is correct. It does not. It has a path at join. Okay. Now let's dissolve the state data by region like we did in the previous lesson as soon as it's done reading in our data. Simplify dot to preserve follow G equals true. Roads CL equals GPD clip. Any roads, country bound US simp. And then roads CL.CRS equals any roads.CRS. Finally, let's dissolve the states by region. Found US dissolve by equals region. Cool. Now let's do some spatial joins, just as you would in ArcMap or QGIS. And you do that using the sjoin method. So let's join the methods with or the roads with our regions. So we can do that like this. Roads region equals gpd.sjoin. Roads CL regions ag. How equals inner. OP equals intersects. Now let's do roads region. Feature class index right. A land dot head. And now we can see some information about our spatially joined data. And you can see here we have another deprecation warning. So it's using predicate instead of OP, which is fine. Don't worry about it for the sake of this lab. So now let's plot our data. But first, let's reproject to Albers. Projection. Country Albers equals country bound US.to CRS. Init EPSG 5070. Roads to Albers equals roads region to CRS. Init EPSG 5070. Oops, extra quotes there. Unnecessary, which is what's causing the error. Cool. Now let's actually plot this data. Big X, PLT, subplots, big size equals 12 by 8. Country Albers dot plot. AX equals AX, alpha equals 1. Color equals none. Edge color equals black. Z order equals 10. So put it behind everything basically. Roads, Albers dot plot. AX equals AX. Column equals index right. Legend equals true. Now let's ledge AX dot get legend. Ledge dot set bbox to anchor. This is really just to adjust the position of where the legend is on the figure. AX dot set axis off. PLT dot axis equal PLT dot show. We got a typo. Let's figure out where that happened. Country Albers. Plot. set aspect. Interesting. Let's try it with their code to see if I just typed something wrong. Yeah, I think I just I typed something wrong. It's fine. But you can see we have a pretty nice figure with the roads color-coded by region, which is pretty cool. And we could further customize our legend to have lines instead of these circles, but for the sake of this exercise, that's fine. We can skip that. However, let's calculate how much road length is in each region real quickly. So we'll do PD options dot display dot float format equals. We want 4 decimal points of precision. Now let's do road. Albers length equals road Albers index right length. Yeah. Now let's do road Albers dot group by index right. That's some. And then road Albers RD length equals road Albers dot length. Sub equals road Albers RD length index right dot group by index right sum. That's so now you can see something is not defined, which is fine. Roads, it should be roads. Let's try that again. Nice. So we can see the road length per region. Very nice. That's it for this mini lesson. Let's keep pushing on. Let's save our changes and do the last one of the day and get on with our Saturdays. Okay, we can see that our changes were persisted. Let's double check in the repository. Yes, join attributes. All right, let's do the last lesson of the day. We'll call this notebook missing data.ipynb. Open it up, select the 3.10.13 Python kernel, and jump right into it. Another short one, jumping right into the code. Let's do it. Import OS, import numpy as MP, import pandas as PD, import geopandas as GPD, import earthpy as ET. Data equals ET data, get data, spatial vector lidar. Oops. Don't need double here. OS Jadir, OS path, join, ETIO on, Earth analytics. Awesome. Let's import the roads shapefile. Always bad at join. Data. Spatial vector LiDAR. California. Madera County roads. TL 2013 06039 roads.shp. Now let's read that into GeoPandas. Path. Let's keep going. Got an error because I probably spelled something wrong, which is fine. This path showing data, spatial vector LiDAR, California, Madera County roads. And there we're good. Okay. Let's explore the data values to see if there's any kind of missing information or things we should know about. SJR roads dot is null dot sum. So based on this method, there's no nan or none type objects as values in the geodata frame. Let's double check. Type SJR roads RTTYP. Okay, print SJR roads RTTYP dot unique. M, none, 5, and C. So you can see that there's actually a none value in there. So let's handle that. So if the value is of a nan or none type, we can use a specific method called the isNull, and it replaces things. Whereas if it's a none type, we're going to use the fillNah method. And so we're going to use fillNah to replace none with unknown. So I'll show you how to do that right now. SJER roads RTTYP equals SJER roads RTTYP dot fillNah unknown. Now let's print SJR roads RTTYP dot unique one more time. And now you'll see that we have M, unknown, S, and C. So let's display our data one more time just to see what it looks like again. Okay. So you can also remove values, but we're not going to do that today. And there's some optional challenges if you'd like, but that's actually it for this lesson. So let's save these changes, commit them to the repo. Lesson 9. And so with that, we have finished our lab for today. You're all free to continue with your afternoons. I'll be here for a few more minutes to answer any questions, but I think at this point, you should be able to complete the entire lab, even if you just follow the recording, which I'll be posting later today. But yeah, just want to say thanks. Hope today was insightful and useful for you all. But that's all I have. So thanks.
Thank you.
Thanks,
You're welcome.
Alex.
Yeah. And feel free to
Thanks,
stay
Alex.
around if you have questions too. Yeah, you're welcome. See you later.
I have a quick question.
Yeah, what's up?
By any chance, when you import all the stuff, is there a way to like, I don't know, like pin it so you don't have to like always keep retyping like Earth Pi and like OS and stuff like that?
Yeah.
Oh, okay.
Yeah. So yeah, you wouldn't be like in a real world situation, you wouldn't be doing this. It's just because we're kind of doing these examples that they want to, they don't want to assume you have everything loaded in already. So that's why there's
Mhm.
so much duplication of that. In a real world, you wouldn't really be doing that in the same way. You do it once and then just do stuff, if that makes sense.
Or something, or like instead of like retyping that all the time. Yeah, for
Well,
sure.
you just have a script, you know what I mean? That it just
Hmm.
automatically loads everything in and then you can do your stuff. That's the whole
Hmm.
point. It's like you can automate things so you don't have to write that every time, which is
Hmm.
nice. Yeah.
Okay, cool. Well, thank you. Have a
Yeah,
good
you're
weekend.
welcome. Yeah, you too. See ya.
So, you hear me?
Yeah, what's up?
Yeah, I'm not sure if you got my message on Discord. But yeah, I was asking if I could get an extension just because I had a family emergency. Like I guess like the Saturday when like this class started, and I
Oh
just
yeah,
got
no
back
worries.
to campus like last week. I was like super busy like with catching up on school, other schoolwork too. Yeah,
Yeah, no, it's cool. I haven't checked Discord yet today, so yeah, I'll adjust that accordingly. And it should still be the submission is not closed. You'll have
sorry, it's
points.
buffering.
Hello? Can you hear me? Hello? Hello? Can you hear me?
Yeah, I can hear you now.
Okay, cool. Um, so it just by default will deduct late points, but I'll just adjust that after the fact. So as long as you message me in Discord, you're chill. It might just take me
Okay,
like a week or so to fix it, but yeah.
sounds good. And just another quick question or like concern. So for me and my groups, so it's me, Yatseli, and Ritu. Um, that's actually just me and Ritu only. For our like capstone project, we're actually going to be leaving 2 weeks before the semester ends.
Okay.
For like yeah, because like I don't know if you remember, but last year's group there was like another group, Jordan, for their capstone.
Oh, they went, did field work and
Yeah,
stuff.
they went to Jordan. That like last year, one of the groups last year,
Okay, for sure.
that's all like we're like the group who's like doing that project again. So
Okay.
yeah, we're gonna be taking 2 weeks before the end of the semester.
Can the two of you maybe start like an email with me so that we can have that conversation and figure out how to so that you all get the most out of this class too without having to like scramble. You know what I mean? So I mean, um, especially because you're both on the same team. I mean, you're graded individually, but just because you'll both be leaving early, I feel like it might be easier just to coordinate together. Um, but if you wouldn't mind maybe sending me an email about that, uh, even through like Canvas, that would be super helpful, just so I could kind of make a note of that and start planning accordingly. Is that cool? Hey, my internet's kind of dying at this point, I think, but I'll message you after, okay?
I'm good. Thank you.
All right, see ya. Thanks.
See ya.